Hey, this is Horner. We're going to look at number 21 through 30 for the AP Physics 1 multiple choice rotational motion pretest. You have a 2 kilogram object moving in a circle. The radius of that circle is 4 meters and the constant speed is 3 meters per second. There's a net force of 4.5 newtons that acts on it. They want to know what is the angular momentum of the object with respect to the axis perpendicular to the circle through its center, which just means that your angle would be 90 degrees. So for number 21, they give you this force, but it has absolutely nothing to do with the problem. We know that the equation for angular momentum is L is equal to m times v times r times the sine of the angle, but since it is perpendicular, that sine of 90 degrees just becomes 1 and we can ignore it. So let's go ahead and just plug everything else in. Our mass is 2 kilograms. We know that our constant speed is 3 meters per second and our radius is 4. So 4 times 3 is 12. 12 times 2 would give us 24. And so our answer here is 24 kilogram meter squared per second. For number 22, we have a wheel. It has a radius of r, so you'll see the r here, and it's mounted on a horizontal frictionless axle so that the wheel is in a vertical plane, so it's up and down, and it can spin this way. 3 small objects having masses of m, big M, and 2m respectively, they're mounted on the wheel as shown above. If the system is in static equilibrium, which means that all the torque should equal the same thing. What is the value of m in terms of big M? So for rotational equilibrium, we know the torques should all be equal to 0. So let's think about the clockwise torque. The clockwise torque here is going to be equal to 2 times big M, so there's 2m, times g times big R. So that is the clockwise torque, and it's because on this side, this mass will pull the wheel down and it should go clockwise. So that's a negative torque, and that's for the right-hand side. For the left-hand side, we actually have 2 torques. One of them is M, and the other one is big M. And so we've got to go ahead and put those in. So this is clockwise, counterclockwise torques are little m times g times r. And then this other one, because it's at a 60-degree angle, we have to use that 60-degree angle. And so we're going to say that's plus m, that's big M, times g times the radius again. And that is times the cosine of 60 degrees. And it's the cosine of 60 because we need it in relation to, we want this side right here, which would be the adjacent side. All right, so now that we have all of that, we'll go ahead and we can say that this guy right here is actually equal to 1/2 of mgr, because the cosine of 60 is 1/2. So let's go ahead and set everything equal to each other. We can say that if it's in static equilibrium, the sum of the torques should be equal to 0. And so we've got 2 torques going clockwise, counterclockwise, which are positive, mgr plus 1/2 big mgr. And we subtract from that the 2 big mgr, and that should be equal to 0. So now at this point we have 2 big M G big R is equal to little m times little g times big R plus 1/2 of big M little g big R. And so if we solve now for little m, we're going to find out that that is 3/2 of big M. Okay, so what did we do to do that? We got rid of all the G's, we got rid of all the R's, and then we, to the other side, we subtracted 1/2. So 2 minus 1/2 is going to give you 3/2, which is 1.5 big M. And so that is the answer. We need to look for that answer, and you'll see that it is letter C. So that's number 22. Going on down to number 23, it is the next question. 23, we have a rod, horizontal tabletop pivoted at one end, free to rotate. There's a force applied at this other end. So Here we've got a length, we were applying a force, and if we applied it perpendicular to the rod, at what distance from the axis should it be applied in order to produce the same torque? So this one, believe it or not, is really simple. All we have to do here is if we know it's 90 degrees, we just have to do L sine of the angle. And that's just the definition. So we know basically here that torque is equal to R times F times the sine of the angle, and so the torque here would be equal to L times F times the sine of the angle, and since we're doing it perpendicular, we'd have the torque is basically just equal to X times F, and so that's equal to LF sine of the angle, and so now we know that X has got to be equal to L times the sine of the angle. So torque is equal to, this is our distance times the force, and so we know that LF sine of the angle is equal to the torque, and so now we could say LF sine of the angle is equal to X times F is what we did. The F's cross off, and our X then is just equal to L times the sine of the angle. Kind of a long way of going about trying to explain it, but that is why you can do that. For the next one, which is number 23, actually, that was 23. Let's go on to 24. For number 24, I got a couple of questions here. It says a solid cylinder of mass M and radius R has a string wound around it. A person holding the string pulls it vertically upward as shown above, such that the cylinder is suspended in midair for a brief period of time. For that time interval delta t, and its center of mass does not move, so it just stays there. The tension in the string is T, and the rotational inertia of the cylinder, and remember we said that always give it T, is 1/2 mr squared. So for number 24, this one is a really challenging problem, and essentially the net torque here is not zero, and it's because there's some acceleration here. So let me just show you kind of what you need to do. The net force here, the net force is equal to the tension minus the weight of that thing, and that should be equal to MA, all right? And therefore, if we want this whole thing to work out, that force must be equal to 0. So if the M times A is equal to 0, then our tension is just equal to mg, and so our answer here for this one is 0. So the net force is actually 0. So where it says net force is equal to 0, that's what you get. For number 25, this one is really complicated, and so what we'll do is we're just going to give you the answer for number 25. Number 25 is actually B. So the acceleration of the person's hand during that time interval needs to be 2 times the acceleration due to gravity. And it's 2 times acceleration due to gravity because there's both a rotational unwinding of the string and it's dropping. And so the rotational unwinding essentially needs to be equal, is that rotational unwinding sends the disc down, and the other thing that sends the disc down is gravity. And these two things are actually equal to each other, so we need to have an acceleration of 2 times g in order to push it back up. So that's kind of the reasoning, but these two are very difficult, and just really going to give you the answer for both because they are so difficult, a little bit harder to explain too. And then those are your freebies for this one. For number 26, you have a sphere of mass m, radius r, and a rotational inertia I, and you're releasing this down an inclined plane. So it says if the plane is frictionless, so if there's no friction on the plane, they want to know what is the speed of the center of the mass of the sphere at the bottom of the incline. So this one really looks really difficult, but it is not. This is actually a pretty good one. The sphere really, if there is frictionless, the sphere never rolls. In essence, it just slides right down the hill. And so we said that this uses conservation of energy. So the energy at the top needs to be equal to the energy at the bottom. And we know the energy at the top is all potential, so it's mgh. At the bottom, it's all kinetic, so it's 1/2 mv squared. And if you cross off the m's and solve for v, you'll get the square root of 2 times g times h. Just a really silly problem. It'd be the same thing as just having a block here, and that block would just slide down. So we know the energy at the top is all potential due to gravity, and at the bottom is just kinetic. Now, number 27 says, if the plane has friction, so the sphere rolls without slipping, what is the speed of the center of mass at the bottom of the incline? This one is a little bit different. This one, you use energy conservation again, but your answer is not going to just be 2gh. What's going to happen here is we have both kinetic energy that's linear, plus we have to do the kinetic energy that is angular, so the rotational kinetic energy. So to do that one, what we'll do is we're going to switch to just a blank slide here so we can kind of see what's going on. We have a height for our little ramp here. We've got the ball at the top. It's rolling down so that when it gets to the bottom, it has a speed going like this, and it also has a speed going in this direction. So there are two speeds here. One of them is angular and the other one is not. So we know the energy at the top is potential energy due to gravity, and the kinetic energy at the bottom is both linear, and we said it is also angular. So at the top, our energy is big mgh, and that's equal to 1/2 mv squared for the linear part, and that's at the center of mass, plus 1/2 I omega squared, which is the kinetic energy of the rotation. At this point now, what we can do is go ahead and plug some things in. So we're going to say mgh is equal to 1/2 of mv squared plus 1/2 of I. Now, omega here, remember, can be linear also. So if I want linear speed, this is linear. I need to take my angular speed, which is omega, and multiply it times r. So if I do that, my omega squared here now becomes just v over r, and I've got to square those. So let's just use a small r up here, and that'll keep it pretty consistent. So there's my equation. I can now take this and I can combine some terms. I know that if I've got all this, I can factor out a 1/2. I can also factor out a v squared, and then I can replace all my other terms. So that'd be m plus, and I have I over r squared. And then if I solve this whole thing for the velocity, my velocity then is going to be equal to the square root of 2 times big M times G times H. So all I did is multiplied both sides by 2. And then I'm going to divide by this thing. So it's M plus I over R squared. And you can actually then move this R squared, and we can multiply both the top and the bottom by that if we want to. But just remembering this equation, going back to what we were doing before, you'll see the only one that looks anywhere near remotely close to it is this one. And so that is the final answer for number 27. For number 28, it says I have a wheel of a 1/2 meter radius that rolls without slipping on a horizontal surface. Good, so we don't have to worry about energies here. The axle of the wheel advances at a constant velocity, moving 20 meters in 5 seconds. They want to know what is the angular speed of the wheel in radians per second about its point of contact on the surface. So for number 28, we can use our equation. First off, we're going to convert all the angular here. So I got to be able to click that. We're going to convert all the angular to linear. So we know that V is equal to omega R. So that would be 20 meters. in 5 seconds, and that's equal to 4 meters per second. And that's just, here's what we're doing. We're just finding this v speed. So now we know the v speed. I know the angular speed then is equal to v divided by the r. And our velocity now is 4 meters per second. Our radius is 0.5 meters. And so now we end up with our answer of 8 radians per second. And so that would be letter C. Next question is number 29. And for number 29, we have a skater who's kind of going along. And a long board is, this board here is free to slide on frictionless ice. So as shown in the top view, a skater skates to the board and hops onto one end. That causes the board to actually slide and rotate. In this situation, they want to know which one of the following occurs. So if you think about this, the whole thing is a collision. And the collision that we have here is inelastic. And because it's inelastic, we know in inelastic collisions, kinetic energy is lost. So this is not right. That kinetic energy cannot be conserved. The linear momentum and the angular momentum are both conserved, okay? Linear momentum here, it says angular momentum would be conserved for this. So A and B is wrong. A and B cannot be right. So linear momentum is not converted. Kinetic energy is not converted into it either. Answer C is wrong because there's no rotational kinetic energy. So the only one that is correct is linear momentum and angular momentum are both conserved in this. So that one is letter E. And then finally we have our last question, and this is number 30. We have two blocks that are joined by a light string. They pass over the pulley, which has a radius. T1 and T2 are the tensions. And so the blocks are going to accelerate. There's no friction here, so we know that this whole system is going to move to the right and down. That would make this pulley go this direction. And we know that the net torque, so the net torque here should be equal to the angular momentum of the pulley times its acceleration. Now, if it's going to the right, we know that the overall net torque here is going to be negative. So that would also make our acceleration negative. So we're going to just say the net torque here is equal to negative I times alpha because our angular acceleration and our torque here is going to be negative. Knowing that, let's go ahead and look at this system. The T1, the first torque, is pulling on the wheel of radius r. And we said that torque is equal to a force times the line of action. So here's our line of action or our radius from that pivot point. And for T1, because it's going to the left, we're going to say this is torque 1 and it's positive. Going to the right, this torque is negative. So number 2, this would be the force for number 2 times the radius of the wheel. So let's put these in the terms that they've given us here. So this would be positive, and then it would be torque 1 is equal to, now our force would be M1 times G, and then we have to multiply that times our radius r. And then for the second one would be T2, torque 2, and this one would be M2 times G times R, and we know that this is going to be negative. So this one will be negative. At this point, we need to go ahead and set up our equation. So we know the net torque is really just the sum of the torques. So let's do the torque that's positive first. That one will be M1 G times R. And then we're going to subtract here the second torque, which would be T2, which is negative. Well, we're subtracting it, so it's already negative M2G times R. And that's equal to my I, negative I, times alpha. And so at this point, what we can do is we know M1G is really the first torque, is what it's going to do. It's the first tension, and we're going to multiply that times the radius. minus our second tension, which is T2, and that's times the radius, and that's equal to negative I times alpha. So if we are going to look at this equation, notice that we don't see it anywhere here because we've got a negative here. Let's get rid of the negative. To get rid of the negative, multiply the whole thing by the negative sign, and now we end up with this equation. So this equation is very, very similar to the one where you have T2 minus T1. And so it is not letter B. You'll see that letter B is T1 minus T2, so it's not that answer. It's actually this one, which is T2 minus T1. So T2 minus T1. We had to recognize that because this wheel's going to the right and clockwise, that our acceleration is negative. We know that we said negative going down here, and then this one is trying to pull to the left, which would be a positive torque. So in the end, it's going to the right, and our final answer is letter D. And that is the end of all these questions.